So now let's focus on a couple of joints here. I'm going to focus on the knee. I mentioned briefly what the knee does during both the loading response as well as during the swing phase, but how does that look kinematically? Now, one thing I failed to mention earlier is that this patient or this athlete has essentially reflective markers on the body, and I mentioned this quite a bit during class. These markers are picked up by motion capture cameras around the lab here. Those are essentially gives us XYZ, three-dimensional locations of those markers. Those markers using a biomechanical model gives us locations of joints, or more specifically the axis of rotations of the ankle, the knee, the hip joints, for example, as well as the segments, the feet, I should say, the tibia, the femur, the pelvis, etc., etc. By extension, we could then measure three-dimensional kinematics of the joints: flexion, extension, abduction, adduction, and internal external rotation. And so for the knee, we're just going to focus on knee flexion extension. So this data, this lab, has the ability to give us dynamic kinematics. That means it's the kinematics or the motion of the joint throughout the gait cycle. And this is something I'd like for you to get used to. It's particularly if you're planning to go to PT school or OT school, where more than likely you will study gait analysis quite a bit. As I mentioned earlier, we normalize the gait cycle from 0 to 100%, so we put all the kinematics and kinetic graphs according to that normalized gait cycle. So this is typical knee flexion extension during the gait cycle for normal walking. Couple of areas of interest here is this initial loading response knee flexion that I mentioned earlier, as well as the peak knee flexion during the swing phase. You know, one of the things that we used to do at the motion analysis lab, I used to run the gait lab at Rady Children's many years ago, is that we would sit down in a lab as a group, and as the engineer, the kinesiologist, the physical therapist, and the surgeon, and we'll go over the patient's data, which includes this type of information, and we just essentially make our interpretations. And one of the interpretations that we'd make is we look at the range of motion. And more specifically, this is known as the dynamic range of motion, where you're simply looking at the max, in this case flexion magnitude, and the minimal magnitude. In this case would be close to 0. So the dynamic range of motion for this individual is roughly 65 degrees. So 0 to 65 degrees of knee flexion during the gait cycle. So as I mentioned earlier, that loading response knee flexion that occurs during weight acceptance, we typically see that right around 20 to 25 degrees of knee flexion. Remember what's happening here. This is early stance. This is from foot strike until opposite toe off. And I mentioned earlier that the ground reaction force is posterior to the knee joint. Look at this illustration. Because it's posterior to the knee joint, that will essentially induce knee flexion. We call that a knee flexor moment, or knee flexor torque, that is due to the ground reaction force, more specifically the vertical ground reaction force. This is known as an external knee flexor moment. So in response to that, your muscles, and more specifically your quadriceps, eccentrically fire to create a knee extensor moment, knee extensor torque. So that is the response. That's controlled knee flexion that I was discussing earlier. Okay, so that's the knee. Now let's take a look at the ankle joint for the same patient, for the same athlete here. So just visually look at it. You can see that dorsiflexion increases as you go from foot strike all the toe off, and then dorsiflexion again during the swing phase in order to clear the toe. So this is how it looks graphically. Again, take a look at 0 to 100% of the gait cycle here. This is ankle dorsiplantar flexion. And one of the first things that we take a look at here is this initial bump here. Sorry, it is freezing up there. This initial inflection in the graph, you can see that positive on the y-axis represents dorsiflexion, while negative represents plantar flexion. So initially, for normal walking at heel strike, your ankle will naturally go into plantar flexion. That is otherwise known as a heel rocker. It's a very important mechanisms by which your body, or more specifically your foot and ankle, responds to impact of hitting the ground. This is part of the weight acceptance mechanism. So that heel rocker is very important. So we typically like to see right about 5, maybe 6 degrees of plantar flexion to facilitate heel rocker here. Now, during the single limb support, the tibia, as I mentioned earlier, is now moving over the talocrural joint, and so therefore there is an increase in dorsiflexion here until opposite foot strike and what we call pre-swing, and then now the ankle begins to toe off. This is active plantar flexion. And then during the swing phase, you can see the increase in plantar flexion here, but then there's also an increase in dorsiflexion in order to clear the toe. It makes sense, right? We've seen patients who have a drop foot, where they have essentially a weak or paralyzed tibialis anterior, so they can't dorsiflex the way they should, so they develop drop foot and maybe may actually drag the foot during the swing phase. So what we want to see is adequate dorsiflexion during the swing phase in order to clear the toe. So again, the dynamic range of motion for the ankle joints, you just simply take the maximum value minus the minimum, in this case plantar flexion, dorsiflexion to plantar flexion, and you get your dynamic range of motion for the ankle. So to illustrate what I was just talking about here, so this is late stance or terminal stance. This is right around toe off here. You can see that the ground reaction force is anterior to the ankle joint here. This is your talocrural joint. So naturally it will cause your ankle to go into dorsiflexion. So in response, as I mentioned earlier, your gastroc, your triceps muscles all have to fire in order to counter that dorsiflexor moment created by the ground reaction force by essentially making an internal plantar flexor moment. Remember what I mentioned earlier in the semester when we were talking about torques and moments, joint moments more specifically. If you ever get confused about torques or moments, remember this is a torque is the turning effect of a force applied a certain distance away from an axis of rotation, a perpendicular distance away from an axis of rotation. So it's dependent on both the magnitude of the force itself as well as the moment arm, right? As illustrated here, it is 9 centimeters. And so if you ever get confused on what that torque is about, think about anatomy. Think about what your muscles do. You're very good at this. You already know what the quadriceps do, what the rectus does, what the gluteal muscles, the glute medius and glute maximus, as well as your gastroc and soleus. So think about your anatomy, think about what they do, and then you'll understand the torque that they create about these joints. So going back to the ankle joint, your plantar flexors are involved in order to counter the dorsiflexor moment created by the GRF here. So that is first of all controlled dorsiflexion in the second double limb support phase, and then as you go into toe off, those same muscles would then concentrically fire in order to push off during the toe off in the beginning of the swing phase. So anyway, that's the gait cycle, as well as the kinematics involved for the ankle and knee joints, and hopefully you had a better sense on how to look at walking after this module. Thanks.